All right, it's another study session again, and today I'm very excited to talk about this Tornado Cash. I think which has been kind of become famous or notorious depending on how you look at it. And just big disclaimer. So today we just focus on the technical side of things, how it works under the hood, and we're not saying people users should mix a coin or anything like that. So let's just get that out of the way. And let me share my screen here quick. Can you see my screen?
Yep.
Okay,
Yeah,
that's good.
Mm-hmm.
All right. So basically, for people who have not heard about this application, is basically a smart contract running on top of a Ethereum blockchain. So what it does enables you to so-called mixing service. So basically, on Ethereum, because it's account-based, everybody just posts the unique account associated with the identity. So if people know your identity, they know your one account address, and then they can pretty much track all your financial transactions, which is not very good. I mean, this is how it works on Ethereum, but on Bitcoin, we have the UTX model, which is more private in the first place. So anyway, so they come up with this idea, Tornado Cash. So what it enables you to do is basically just any other mixing service. You are hiding in the crowd. So let's say, it's like you think about it as a pod. It's a collective pod. So everybody, let's say, put one Ether into it, and then later on they can withdraw Ether out of it. And the difference is, when you withdraw it from it, you can withdraw to any new address, right? So in this way, you're kind of obfuscate your trace per se, right? So it's like in a physical analogy, it's almost like you are in a village. Every villager, they have there's almost like a public square. There's a big jar there. Everybody deposit $1 there, and later on you can take $1 out. So because you are mixing this with the whole full village, so hopefully people who cannot identify which $1 originates from you. So that's a high level idea. So how does this work? I think this is very interesting technical work I'm going to cover. That they have we are going to go through a few iterations of design, and each design has some flaws. Then we are just going to tackle them one by one. At the end, you can have a very anonymous mixer. Basically, if Alice deposits some cash into the big deposit, and then she can withdraw the same amount later on, and nobody can link this deposit and withdraw transaction. Is basically it's impossible to link them. So that then you can make a transaction more private. That's a thesis. So how does it work exactly here under the hood? So for example, you have Alice here. So basically each person come here with a unique number. You can think about it as a secret. I think that's a one called nullifier here, but let's not worry about the term. I'm going to cover why we have this term and how does it work later on. But for now, just thinking every user, they locally generate a secret, almost like a private key. So basically you generate some random number. It's unique and only yourself knows it. So when you deposit, you just hash it, and then you send it to the contract. So think about this. The contract almost has two parts. First part is basically the deposit, almost the vault, which keeps all the money people have been sending. So this is almost like a vault. The other part is keep track of the state. For example, this Alice, he hashes secret. It become 0x 1 2 3 4 whatever, and then he deposit Ether here, and then it shows up in the contract. Okay, so the same process. Bob can also deposit, and then maybe ends up with 4 5 6, and Charlie, the bearer, also can deposit into here and become, let's say 7, 8, 9. Okay. So far, so good.
Yep.
Okay. Yeah, almost like in this case, it's almost like a UTXO model. Everybody has a node. Each node is like this. This hash is almost like a serial number, and the only thing is, only the owner knows the preimage for this hash. So later on, they can use this as a proof to say, hey, this node, I do have one node here because it's in this list. So we just talk about the deposit, and then, I mean, of course, later on, let's talk about how do they withdraw. So if Alice previously has deposited 1 Ether into this, vault contract, and now she wants to, withdraw, so you can just send, hey, I have this secret, I know this secret, and this secret hashes to, 1, 2, 3, and the contract is going to check, hey, it is in my list of available nodes. I will just allow you to withdraw 1 Ether, right? So this definitely works, right? But there has some problem. Can you see what problem this has in terms of the Tornado Cash thesis? Any guess?
Well, if the contract knows, like, okay, you committed 1 Bitcoin with hash 123, and then you withdraw with that same hash, then can't you just, you don't need to know the in-between steps. Okay, Alice deposited here, and then she withdrew here to a different address.
Exactly. So basically, you can link the deposit with the withdrawal, right? So then you are not mixing, right? Because this is deterministic. So that's why we can identify as Alice, because Alice's hash, when we know when she deposits, we know Alice's hash is 1, 2, 3, right? And then if somebody withdraw, even we don't know this is to a new address, we know it's probably Alice or somebody Alice wants to transfer to, right? Because we can use this deterministic hash to link these two transactions, which is not good, right? The whole point is to obfuscate, to make these two unlinkable. So definitely this does not work, right? I mean, naive solution. So that's why we come up with some new ideas how to break this. And by the way, there's another assumption here. No, not assumption, like there's another requirement when you deposit, you have to deposit a fixed amount. I think in this example, we just make it 1 Ether. Does anybody know why this is the case? For example, here, I think this is implicit. Basically, everybody has to deposit the same amount. For example, maybe Alice, if not, this is not the requirement, Alice can deposit 1 Ether, Bob 2, and Charlie maybe 100. Why is this? Is this a good idea? Make anybody who can deposit whatever amount?
No, because then you can determine who deposited what.
Yes, exactly. So for this purpose, for people who do use this mixing service, everybody has to deposit the same amount. So you can link using amount, right? So basically you have two types of information, the amount and also kind of like an address. So in this two, so we just talk about, so one way to hide this is say, hey, everybody deposit the same amount. So you cannot link using amount information. So that's out of the way. But what if we just using this naive approach, but this seems not working, right? So what can we do? So that's where the zero knowledge part, kind of the magic part coming from. So instead of saying, hey, I have this secret, which is hashes to this, 1, 2, 3, that means I've deposited before. So you must allow me to take some money out. So we cannot, you don't want this to be linked to a certain hash here, right? But also you want to make sure it does hash to a certain, one of this, right? Because otherwise, what's the issue? Let's say if I just say, hey, I submit a proof saying, I just submit some random proof can you just why not just then there's no identifying information there, personal information. Can I just use that? Just some random proof? What's the problem? Can you see the problem? So let's just submit some random proof. I don't constrain any. I'm not showing it, what proof this is. You can just allow me to withdraw. Is this an issue?
Brandon, you're having microphone problems again.
Yeah. Jay, maybe you want to chime in? I just submit some random proof and this contract allow me to withdraw. Is this an issue?
Yeah, wouldn't it need to be like a specific, it can't be a random one, is that correct?
Yes. So basically you have to at least say, hey, I know some secret. If you hash it, it is one of this, right? But I'm not going to tell you which one it is. This is much better, right? Because now you cannot easily link it. Does this make sense? So basically you're generating a zero knowledge proof. In this proof, the good thing is you are proving you know some secret which hashes to one of this, but you are not telling me which it is. Because if you're not using zero knowledge, if you use any other way, you tell me the secret, you hash it, it's going to link to one of this, right? It's almost like a group signature. You are just signing on you are one member of the group, but I don't know which group you are. If you know this concept, I can only prove I know some secret. If I hash it, it's one of this, but I'm not telling you which one it is, but it can still prove it is one of this, right? There's no other technique.
Okay, now I understand what you're saying. Okay, that makes more sense. Okay.
Okay.
So you could prove that the zero knowledge proof that you have is associated to one of the hashes without revealing which hash it is. Yes,
exactly. Then they are you're breaking the link between the deposit and withdrawal, right? Because the whole reason why it's linked because it's the same hash. You can use this hash to link these two transactions.
Okay.
Okay. So is this the end of it? I mean, so if I submit let's say zero knowledge proof, which is what we hinted at in the last slide, right? So I just say, hey, if I'm Alice, I want to withdraw to a new address. I just submit you to a new proof that says, hey, I know some secret, I hash it. It's one of this, but you cannot know which one it is. Okay. So is this the end of it? Can you think of anything that's maybe a problem? Want to have a guess? So I use basically the contract it does is very easy. When somebody tries to withdraw, you just check, hey, is this proof legit? You just verify this proof, this zero knowledge proof. Is this proof good? If it's good, this guy knows some secret that's hashed to one of this, but I don't know what it is. So if it's legit, if this proof is valid, I'm going to, pretty much just allow this withdrawal of 1 Ether.
Okay.
Is any issue with this scheme? I don't think now it's much better, right? Because you don't know which one links, right? You don't know which deposit links to which withdrawal.
I guess you would have to do it all simultaneously for all the users, because if you just do it one by one, you could just compare like, okay, this hash is missing. And so then you can make correspondence and say that this hash belonged to this person if you just do it one at a time.
It's very close. So basically here, right now it's after, let's say Alice withdraw. Alice is here, right? Bob and Charlie. So if Alice withdraws, so this thing is still there. You see, we're not, the contract we just mentioned so far, It's not deleting anything. You see what I mean? Even after withdraw. But you clearly
Okay.
see this as a problem, right? Because
Mhm.
you know, if we're not deleting after withdrawal, what's the issue? Can you see? Can you guess? Let's say I'm Alice, I withdraw here. What if I do it again, right? You know, I have, this is like, let's say attacker.
Oh, okay.
You see what I mean? You can,
Yeah.
I can deposit 1 Ether, but I can keep submitting because there's no check here, right? You know, you just say
Yeah,
this,
okay.
is this proof is legit or not? But it's not saying, hey, has this money withdrawn before? Because everybody can only, it's only entitled. This one hash, the pre-image of the one hash, only enables you to withdraw 1 Ether, right?
Mm-hmm. So you
So
just
what's,
could, Mhm.
go ahead. What's the issue
so,
here?
so that's the issue right there. The fact that it's not being deleted, there's no tally being kept. You could just keep requesting to withdraw over and over again if there's no like actual tally being kept.
Yes, exactly. So that's, you know, we have the first version, which is linkable, and then we use 09, specifically ZK snarks to break the link. But then we have a new problem, right? And then we don't know because it only shows us you are one of this, but you're not telling me which it is. So even for this contract perspective, it doesn't even know which one, you know, the 1 Ether is being withdrawn, right? Because it only says one of this. I don't know which one it is, right? But then that's a problem. You can pretty much replay it, right? So if I have this, I can just keep, I can just keep, you know, with getting cash out of this, and then it's not good, right? So that's why we need to another mechanism, just almost like a flag saying, hey, which one of this, you know, has been withdrawn. But at the same time, we cannot identify it. So that's where I think the cleverness, I think one of the, you know, the ZK stack is one huge, you know, technique in Tornado Cash. Another one is a very popular scheme, you know, basically called the nullifier, which I hinted at before, right? So if you remember, you know, if here, not only we hash a secret, but also we hash it together with the so-called nullifier. So that's where the nullifier coming into play, because without this nullifier, you can also, you know, attack by replaying the same transaction. You can withdraw, you can pretty much, you know, empty the whole vault if you only have any, if you only deposit even ever once, you can withdraw the whole thing. So the nullifier, how does this work? So you have this N, you know, this is a secret, and this is your N, which is a nullifier. Almost like a nonce, right? Yeah, pretty much it's a unique number that's pretty much just used once. So what does this do? So instead of hashing the secret only and ends up with these numbers, you also hashing it together. This is concatenation you can think of with a nullifier. So you end up with this. And then what do? In the proof, you are not only saying, hey, I know there's two numbers, the secret and the nullifier, you know, hashes to one of this, you know, but also though a nullifier, you know, I know the hash of this nullifier. So the contract, besides storing all this, is also going to store a list of nullifiers.
Okay.
So when
you
you
can only use
withdraw,
Mhm.
so let me finish and then I can clarify. So basically you have a list of nullifier here. So when you withdraw, you're crossing out, pretty much you are marking, you're pretty much like crossing every nullifier that's been already withdrawn. Okay, so you know, kind of, even though you don't know which one it is, but you can be sure you can only withdraw once. Because why? The contract is going to check not only the proof is good, but also the nullifier I have not seen this nullifier before. So now you can be sure you can only withdraw once. Does this, I know this, for people who have the first time heard about this nullifier, it may be a little bit of a, I think it's It's a very clever trick. Do you see what I mean here?
Yeah, it makes sense. So you can only use the nullifier once to prove that you have a correspondence with the hash.
Yes.
Mhm.
Let
Is my mic working better right now?
Yeah,
yes.
way
Now
better.
it's good. Sounds good.
Yeah. Sorry about that. I might have missed this part, but why can't you just have a list of hashes that you cross out?
Okay, here's the thing, right?
I-
So let's say we go back here. Let's say we don't have the nullifier, okay? Every time
Yeah.
you withdraw with the proof, here's the thing, right? The contract doesn't, in the proof, it only says, I know the pre-image of one of this, but I don't know which one it is. So there's no way to,
Okay.
for me to pretty much cross out here, right? So that's the first one.
Mhm.
So even if we can cross out, then you are like expose yourself, right? Because the whole point for the zero knowledge here is to hide which one it links, right? So if the contract somehow still not can figure out which one it corresponds, we're back to square one again, right? You see what I mean?
Right.
If you say withdraw this, I cross here, I know you're Bob, you're not Alice, you're not Charlie, okay? But then we have another problem. You can all keep replaying. So that's a nullifier problem, where it comes from. So let me ask you guys this.
How,
Go ahead.
so how does the contract get a list of nullifiers? Like when you deposit, is the nullifier added to this list?
Okay, that's a very good question. I think that's what I'm about to ask you guys. So what do you think? What do you think if let's say when I'm depositing, I put my nullifier there. It's a list of nullifiers. Is
Well,
this
then
an issue?
yeah, because then you're back at square one, right? Because
Yes.
you're,
Yes.
yeah.
So because then you can use the nullifier to link these two transactions, and then not good, right? So what
Right.
do you think? Oh, can you think of one way to remove this thing, to still have the nullifier, but you're not able to link these two? Yeah, this is very.
Another ZK Spark with the nullifier.
No, I think that's you're just like putting pretty much the turtles all the way down. So I think. So Jay, do you want to guess? Like how? Because yeah, Brandon just pretty much this is my question when I first heard about the nullifier. I think yeah, because if you put the nullifier in the deposit, and then you are proving here, and then you are crossing it out, it doesn't then go back to the first. We are going back to square one again. What do you guys think? How do you
Well-
break this link?
But what do you mean by going back to square one? Is it that you can make a correlation between who the
Yeah,
hash
because
belongs to?
yeah, because if let's say Alice has a nullifier hash to 1 2 3, right? And then you are using this scheme. We are here. We're saying, hey, we don't know which one it is. We don't cross out here, but we're crossing out here. But here, which Alice's nullifier is here, right? So if you don't cross here, you cross out here, we still can identify Alice, right? Do you see what I mean? I think that's what Brandon is asking.
Yeah.
You can still identify it because you have the
Because
nullifier.
yeah, because almost think about you have two lists of hashes, right? One is the secret plus the thing hash it, and the other list you have is the nullifiers. You hash all the nullifiers. So even if you don't cross out here, you cross out the hash. But the hash, if you put the hash when you deposit, and then when you withdraw, I can still link these two hashes, right? Because it's deterministic. So it should be the same. So which almost defeats the whole purpose, what we've been doing.
Okay. So how do you find a way around that? That's interesting.
Yeah, I think it took me a while to go through the code, but here's a very clever trick. After I tell you, oh, it's obvious. So basically, you don't do this. you don't put the nullifier in the contract as the deposit, but you put it as a withdrawal.
Hmm?
Does it make sense?
Hmm.
So when you don't put the nullifier hash, add the hash when you are depositing. You only put the hash out when you're withdrawing. So basically, when you withdraw, when you deposit, there's no nullifier in the contract yet. So only when you withdraw, you're crossing this out.
Oh,
So that you don't have linking information from, but again, because it's already crossed. So when you withdraw again,
Hmm.
it's going to
So
fail
the-
check.
Okay, so the execution of the contract becomes more expensive because every withdrawal you have to check against every hash that's been committed.
Oh, it's a little bit. I think I'm going to cover more details how this works. I think this is like a design level, right? So we can do a lot of ways to optimize. For example, you can use a so-called hash table, right? Or dictionary. So that's actually how they do it. So you don't even maintain actually an array, right? That's going to be big O n, right? So you instead use a so-called hash table. So it allows you to query, in constant time, amortized time, right? So is this right now? I think I'm going to next cover a little bit of the implementation. But is this the idea now? Is all make sense to you guys? Which
So-
I think is very, very interesting, by the way. Yeah. Go ahead.
so just to make sure I understand correctly, so originally, when we were making a deposit, we were also including with that deposit the hash nullifier. And then when you withdraw the deposit, we would X out the hash nullifier, but then that had a security vulnerability where everybody could see who that nullifier belonged to. So the solution to
Yes.
that,
Mhm.
the solution to that then is that when you make the deposit, instead of including the hash nullifier along with the deposit, you just don't do that at all. You just make deposit without including the hash nullifier. And then when you want to make the withdrawal, that's when you add the nullifier so that people can have a reference to make sure that you're not able to withdraw more than once. Is that correct?
Exactly.
Okay.
That's perfect explanation. Yes. Now you
Okay.
see the whole full picture, right? So now we achieved the original goal. Nobody can link this deposit and withdraw. And also, if you deposit once, you can only withdraw once, and nobody can link it, right?
Interesting.
So, yes. So that's why I kind of, even though it's being sanctioned, I think the technically, I think this many tricks here can also be applied to, many other type of zero-knowledge enabled applications, which is usually think of, we just solved almost two impossible problems, right? One is, how do you say some secret hash to the list, but without telling me which of this one can match, right? That's one almost impossible to solve. The other is, if you only using zero-knowledge proof to show you are one of this, and don't know which one it is, how do I make sure you are not withdrawing more than once? Basically, you are pretty much like a double spend, right? So we just use two techniques. The first one, the zero knowledge, to solve, to break the linkage from my hash to, I'm only saying I'm one of this, you don't know which one it is, but you can be sure it's one of this, right? Second, we use the nullifier scheme, to make sure only one, if you deposit once, you can only withdraw once. And the third, almost like implementation wise, so basically the trick is you're not putting the nullifier when you are depositing, because otherwise you can be linked. So you are only putting the nullifier when you're withdrawing. So pretty much the three tricks put together, you can make sure the Tornado Cash can work. So that also means you can also do the same thing on Bitcoin, right? Because we have all the three tricks we have just mentioned. You can also play on Bitcoin using Scrypt today. So for anybody who is watching, if you would just want to have some fun project, again, I'm not I'm not incentivize anybody who do create a mixing service, but just have good project to work on. Because all these tricks I just mentioned, it can be applied outside of Tornado Cash, right? You see, it's very generic. One is how do you prove
Yeah.
like a members, like a set membership, right? Without telling me which of the member. Second one is, the nullifier, like how do you withdraw? How do you make sure almost like some action only happen once, even you don't know the exact action. Right? The third one is almost
So-
like implementation. Go ahead.
What was Tornado Cash one like master contract, or was there like many different instances of a Tornado Cash contract?
Oh, Tornado Cash, as far as I know, just one. I think it probably has many clones. It's like Uniswap, right? I think Uniswap is just have one Uniswap, but you have all kind of other clones like a Sushi Swap or what swap not, right? So I haven't checked,
Right.
but the
So
most
you-
famous one is called Tornado Cash. But my bet is you probably have many like clones, like a copycats. Because for example, this one, right, enables to only deposit and withdraw Ether. But I think later on they enabled also tokens as well. So they probably have,
Right.
my guess is like all this like most popular so-called smart contract out there is probably has many clones as well, but not as popular. The whole
I could see
point here
this-
is you hide in the crowd, right? So if you are like a not popular, you only have one guy or two. That's not many anonymity gain, right? So the more people use it, the more anonymous you become. Yeah, go ahead.
I see. Yeah, I mean, it could be better on Bitcoin because if the fees are lower, then the minimum or the standard deposit can be much smaller. So
Yes, exactly.
if it's
Exactly.
one ETH, that's really expensive, but if you're using Bitcoin, maybe it's 0.001 BSV.
Yeah, that's what I'm saying. Is somebody just want to have this, almost like a toy example. Yeah, you can actually this whole thing I just mentioned, all the techniques you can do this on Bitcoin and it works better because of the fees, right? And because the fees is much cheaper. For example, here you put 1 Ether in. I mean, technically you get 1 Ether out, but it's not, right? Because you have to pay the fees. So you may only get, I don't know, 0.995 every time you do this. So which again, right, means less people are going to use this. So if the fees are cheaper, you can have more people, which increase the anonymity stat. So we should actually, this works, not only works on Bitcoin, you can actually, it actually works better on Bitcoin, literally.
Is that because of the UTXO model?
Not really. I mean, here it's mostly because the fee is cheaper. So more people can afford it. So the set. So basically the list here is much bigger, right? So you would rather hiding 1 million people versus just 3 people, right? Because maybe the fee, I go to extreme example, the fee is like $1,000. Not many people are going to use this, right? So then, then you are not hiding among the big crowd, right?
This might be a completely separate topic, but I've seen with a lot of the Bitcoin smart contract applications, you have one master smart contract, and so there's a bottleneck because everyone that wants to interact with the contract, they're using this one UTXO chain. So like at scale, that's a pretty big bottleneck. So how do you distribute that into many UTXO chains, or is that even possible?
Okay, yeah, they are hitting the nail on the head. Basically, okay, so two comments. Okay, I think this is a problem I've been thinking of always also on my head for a long time. So basically I would say two answers. Number one, even you are only having everybody have a master contract and only have single UTXO, everybody has to pretty much always using the latest. So you have like a sequential problem here, right? Even in this case, remember, it's still better than Ethereum. This approach is what Ethereum is doing, right? Because Tornado Cash, right? Only one master contract, as you said. everybody has to go through this one by one, right? Right. So that's one. Where I'm saying number one point is even we only have using one master contract in one single UTXO, because in Bitcoin, all the UTXOs are processed in parallel, even though they're chain. You see what I mean? So you're just creating the chain transactions off chain. And then once you submit it to miners, they don't care whether it's chain or not, because all the UTXOs are independent. So that's the number one point is even we use this chained sequential processing as in one master contract, is still more performant than Ethereum, right? Because once you submit it, miners can process in parallel. Okay, doesn't matter if it's chain or not. Do you see this point?
Yeah.
Let's say 1,000 transactions is all chain. Once I submit to miners, they don't care, right? They can process all of them in parallel. I mean, at least the smart contract part. So that's one big
Well,
advantage.
They have to process the chain in order, right? You can't submit
No,
a
I mean,
parent before its
internal.
child.
No. You're probably talking about the UTXO, the US. But the UTXO, yeah, so a transaction roughly process can be two parts. One is checking the UTXO, right? Whether it's spent or not, whether it's, does it exist. So the second part is you're processing, you're pretty much running the script, right? So
Okay.
I'm saying the second part can be in parallel. Do you see what I mean?
Okay.
Yeah. Okay. So again, even using the single master contract, you can still process at least the smart contract part, which is the most intensive part in parallel. Okay, that's a huge advantage. The second part, I think that's why we use the recursive secret snack, the back to the genesis, right? So that's how hopefully we can break apart, a single master contract into different UTXOs. Let's say it's in the simplest example, token contract, right? Right now you can do, one contract, master contract, everybody has to use the same UTXO and chain them together. What if you can almost like a Bitcoin, right? You are breaking them into, Alice has his own UTXO, have these tokens, Bob has his own UTXO, so they're all independent. That's the ideal case, right? But then the challenge there is, how does Alice or Bob know, or if they send to Charlie, how does Charlie know whether this action is coming from the original? So that's again back to the genesis part, right? You see what I mean? So if you break into multiple UTXO, somewhere you have to link it to the original master contract, to the genesis. But now we have a way to do it, right? So basically using recursive snacks. So that's the ideal, almost like a Bitcoin-ish way to do smart contract. And you pretty much break up the master contract into separate, individual UTXO contracts, but you can still be sure it's coming from the original one. Does this make sense?
It's good. I don't think I fully have my head wrapped around it, but it's good to know that you're thinking about it, because that's something I've always thought about. It's like, okay, how do you have an application with 10,000, 100,000 users and they're sharing one UTXO?
Mm-hmm. Yes. Okay. So number one is, I think using the chain transaction, you can go a long, long way. I think you can probably go like 1,000 or even 1 billion users, no problem. But the problem is, you can probably go into show when you have 1 billion users. You see what I mean? Even for the first one, right?
Yeah.
Because generally you just checking the UTXO is not a bottleneck. The only bottleneck is you run this.
Yeah, not necessarily, because let's say there's trouble somewhere in the chain with interacting with the network, then I don't know, it seems like a single point of failure.
Oh yes. Mm-hmm.
So in
I
theory,
would say
maybe.
Mm-hmm. Here's the, that's why I'm saying you may break apart when we get to 1 billion. But here's the thing, right? Usually, then you can have multiple entry points to access this contract, right? Because if you have one contract and you have different apps that interacting with it or using different clients, these clients can pretty much like coordinate off chain, right? Yeah, think, hey, are you at the latest? Oh, what's the latest now? Let's coordinate. And this coordination can have you can have multiple points, right? So you don't have to. It's not as reliable as the blockchain, but you can add multiple servers. You see what I mean? And the coordination
Yeah.
between the servers. But you have a problem if all of them break down at the same time. But it's going to have a long way to go. Still a long way to go. You break down all this technique. So I'm saying I agree. I think ideal case would be the second. You don't have the master contract. You have all the UTXOs have the sub contract, and still. But in this case, the challenge is how do you make sure this sub contract actually link back to the Genesis contract, master contract. Right? So that's what I'm saying. You can use the recursive stack technique we used to solve the back to the Genesis problem. You can apply the same techniques there, but I don't think that people are building a implementation out of that. But I think it's technically possible. Okay.
Cool.
All right. So
Yeah.
let's. I think we just talked about the design. Hopefully, we have convinced you. Okay, this actually works very elegantly. And let's now get that in the rest we can just get a little bit down to the the implementation, because you also hinted if this notifier, let's say, or this hash list gets very big, if more and more people using this, it's going to become more and more expensive, right? The processing wise, so you have to pay more fees. So that's why we in reality it's again data structure wise, we are also using Merkle tree. It always shows up, right? So basically, instead of a hash, the list of hashes, we are organizing them into a Merkle tree, right? So instead of when you check the existence, instead of going through all of them, which is big O N, you can put in a Merkle tree. So you can the complexity is only big O log n, right? Which is much better. So when you generate in the proof, you are not putting the whole tree and generating a proof saying, hey, oh, by the way, so when you organize in this way, so in the contract, instead of seeing this raw hashes, all this shows up in a single like a Merkle root. So in the contract itself, actually, you don't see all the hashes. You only see a single root hash, which is pretty much give you this the state of the latest in all the deposit and withdrawals. So think about this 0, 1, 2, 3, they're all at the bottom leaves. So that at the end, they're organizing the Merkle tree. And only the root of the tree is put in the contract for anybody to check. So when you are actually producing the proof, you are giving the Merkle proof actually.
So off chain, do you need to construct the whole tree yourself?
Yeah. Yes. I think of what actually happens is I think of Tornado Cash or somebody actually maintain this, but maintains this latest tree. But here's the thing, right? You don't need to trust anybody because all the individual leaves, they're posted on chain, right? Because every time you deposit, this is going to show up in the contract. When you are calling the contract, you deposit. So, for convenience, I think some servers maintain this, so you can fetch it and then produce your proof locally. But you don't have to.
Sounds like a honeypot, that service.
Oh yeah, that's yeah, you can. But there's nothing secret about it. This thing is all public anyway on chain. It's just for convenience. The
right.
Some servers they just crawl it and maintain this. There's pretty much, let's say, censorship resistance. Even though let's say you want to query some servers about this full tree. If it censors you, you can always go back to the blockchain and fetch this yourself. You just have to go through every Tornado Cash transaction. and then you can build all the leaves, and then you have the full state. Okay.
Interesting.
So this is actually the proof, when you are generating the proof, you are actually saying, hey, this is a Merkle proof. This is the Merkle tree. I'm not, they use 32 levels, so it's almost like 4 billion entries. So when you're generating the proof, one way, naive way is you have all the 4 billion entries, and then using your leaf, you're producing a proof, and then matches the root, right? This is not efficient, right? Again, you can use the Merkle pass together with your leaf. The proof basically says, okay, I'm using the Merkle proof to prove I'm a set. I'm a member of this big set. So this set, shows up at the root hash. And, this is only for the hash. For the nullifier, actually, if you look at the code, actually it's just a hash table, pretty much a set. So when you withdraw, you put in set, you mark this as already withdrawn. So when you're trying to withdraw again, the counter is going to check, hey, oh, this entry exists and it's been marked that's already spent. So it's going to reject. So 2 implementation. One is you are not maintaining the list of all the hashes. When you for your node, basically you organize in the Merkle tree. And second is, you are not maintaining a list of the hash of nullifiers. You are maintaining you're not putting an array, you are putting a hash table. So you are queried, you can update it more efficiently. But yeah, that's everything about the Chernota cache. Any final comments? Which I think is, it's pretty cool tech wise.
Yeah, that's
Yeah.
interesting. So someone's implemented Merkle trees on script already, right?
Yeah. Merkle tree has been around almost like 2 years around. Yes, it's actually very simple. Yeah.
So basically all the tools are there.
Yes, you have the Merkle root, you have the hash table. We call it hash table. You also have the zk snark. So, it's just somebody. By the way, I think you probably heard about this. We have the hackathon coming. So if somebody wants to just have some fun exercise, I think just implementing all the building blocks there will be very fun exercise. I would say, just have somebody get some Tornado Cash running. Just as a toy example. Anything else?
Yeah. No, this is really interesting. This could be used for a lot of different things, not just like illegal things. This is very interesting.
Yes, and that's why the whole point. I'm not saying, hey, I'm not encouraging people to run another mixer on Bitcoin. I think it's probably gonna one day or later it's going to be taken down. I'm saying you can use we can use the techniques here, right? The zk snark, the nullifier, the Merkle tree, and also the when you're withdrawing, only there you put the nullifier. All these ideas that can be, it's application, agnostic. You can also take this out to build all other kind of like a more legit zero knowledge applications.
Cool stuff.
Yeah, I think very cool. I think it's a very quite a few clever trick when I read it. Oh, okay, yeah, this is good. But now they have been taken down. So we see, I think unfortunately make it more famous. I only check into the details after it's been sanctioned. So
Yeah,
okay.
I didn't think that was gonna last too long.
Yeah. Yes. Okay. Any other closing thoughts?
No.
If not,
Thank you.
Nope.
Okay. Okay. No problem. Okay. And if you have not, for anybody who's watching, we are having the Zero Knowledge Hackathon coming at the end of this month. So I'm going to post in the show notes how to register and check out. You can show off your zero knowledge skills and win up to $45,000. So
Wow.
it's please register, especially who have YouTube. So get because you are like ahead of the curve. So maybe, for example, you can build, the Chernota Cache. Yeah, it's
For sure.
a very strong competitor. Okay.
I'll
All
be
right.
joining for sure.
Okay, thanks, guys. Okay,
Alright, thank
thanks for
you.
coming, and hope to see you next week.
Thanks.
Enjoy the rest of the
Take-
weekend. Okay,
Take
bye-bye.
care. Bye.
See you. Bye-bye.